Welcome to Multivariable Calculus Lesson 4. This is the last of the single variable lessons that were skipped in the BC curriculum. Today's lesson is on the hyperbolic functions, or more correctly, the hyperbolic trigonometric functions. Remember our old friend, the unit circle? Here's the unit circle with radius 1, which makes each block in this picture 1/10 of a unit. And we draw our angle, and the x-y coordinate on the unit circle was equivalent to the cosine of theta and the sine of theta respectively. So let me introduce you to the unit hyperbola. If we draw a box that we used in pre-calculus to help us draw the hyperbola, then you can imagine inside the box would be the unit circle, x squared plus y squared equals 1, and the equation of the unit hyperbola is x squared minus y squared equals 1. And I didn't draw the asymptotes because it made the picture too messy. So we might think that, well, let's draw an angle and put a point on the unit hyperbola, and then let's call x the hyperbolic cosine of theta and sine the y the hyperbolic sine of theta. Well, that's not quite how this works. Because if we did it that way, we'd only be able to use angles from negative 45 degrees to positive 45 degrees, and then we wouldn't be able to use any angles from 45 degrees to 135 degrees, or from pi over 4 to 3 pi over 4, etc. And so we'd have a kind of a messy functions with a limited domain. So that's not the way the hyperbolic sine and cosine are defined. So let's go back to the unit circle and look at it from a slightly different angle. Here's my picture with cosine and sine equaling x and y, but instead of using the angle as such, we're going to look at the region bounded by the unit circle and the angle. Now the entire circle is pi r squared, and we're looking at theta out of the whole circle. So the area of this region is theta out of 2 pi, that portion of the circle, times the area of the whole circle. In the unit circle, r is 1, so that goes away, and the pi's cancel, and we end up with the area of that region being pi over 2. So this is the idea we're going to transfer to the unit hyperbola. There's my angle, there's my point xy, and this area then is going to be theta over 2. This way I can make theta as big as I want, because I can just extend that arrow up the hyperbola and make the area bigger and bigger without bound. And if I have a negative angle, then I use area below the x-axis. Now you can see then that defining it this way, we have hyperbolic cosine of theta being x on the unit hyperbola. That, by the way, is pronounced cosh theta. And so it's going to be limited, its range is going to be limited to greater than or equal to 1, whereas the hyperbolic sine, pronounced sinh theta, is going to be able to take on any value at all. So it's a slightly different way of looking at things, but it's still related to the original trig functions in an area sort of way. Now, it turns out that cosh theta is equivalent to e to the theta plus e to the negative theta over 2. And I will show you why that's true at the end of the lesson, because it's a bit complicated. I don't want to get bogged down in that here. And the sinh theta is equivalent to e to the theta minus e to the negative theta over 2. And I won't prove that one. I'll let you do it. It's a very similar proof to the cosh theta proof. So this way we have two ways of writing our hyperbolic functions. The equation for the unit hyperbola is, as I said, x squared minus y squared equals 1. And so we're not going to prove anything right now. We're just going to show that these other functions do work. If I put the expression for cosh in for x and the expression for sinh in for y, and simplify that algebraically, square it out, take the 1/4, factor the 1/4 out, things cancel, and then we're left with 1/4 times 4, which does in fact equal 1. Now that's not a proof, but it does show you that these two functions make sense. So likewise then, we can state the identity cosh x squared minus sinh x squared equals 1. Notice that's similar to the old one that you're familiar with, cosine squared plus sine squared equals 1 for the unit circle and the regular trig functions. Now there's piles and piles, of course, of identities, which are very tedious to derive. So we won't derive them. We'll just list them. Here are some identities for the hyperbolic functions that you may want to jot down to use during the homework and during the quiz. There's the definitions of the other 4 hyperbolic trig functions, and I know that hyperbolic tangent is pronounced tanch, but I'm not sure about the rest. And there are some identities. Again, these are in your book. You may want to write them on a note card and take them with you to the quiz so that you have them handy. Also to do homework so you don't have to keep flipping back and forth on the pages. Now the derivatives of the hyperbolic trig functions are interesting too. I'll just develop one of them here and then list the others. We can rewrite cosh theta in terms of e, and then we just take the 1/2 out. It's a constant, and so the derivative is just the constant 1/2 times the derivative of e to the theta, which is e to the theta, and then the derivative of e to the negative theta is e to the negative theta times -1. And that, interesting enough, equals sinh. Remember that the derivative of cosine theta is negative sine theta. Here the derivative of cosh theta is positive sinh theta. Here are the other derivatives. Notice that for the main 3 we get a positive derivative, and for the other 3 we get negative derivatives. And again, those are things you might want to jot down. So for the inverse hyperbolic functions, I'm going to derive one of them, namely the inverse of cosh x. So for cosh x, we set up a function y equals e to the x plus e to the negative x divided by 2. For cosh inverse, then, we switch the x and the y. So now we have to solve for y. So the first thing I did was multiply the numerator and denominator by e to the y, and that gives me e to the 2y plus 1 in the numerator and 2e to the y in the denominator. Then I cross-multiplied, and so I got my 2e to the y times the x equals just the numerator. And then I grouped everything to one side, and what I have here is a quadratic in e to the y. So using the quadratic formula, e to the y equals negative b, which our b is negative 2x, plus or minus b squared, so that's the 2x squared, and then minus 4ac, and a and c are both 1, all over 2a, and again a is 1. Now we can factor the 2 out and cancel it, and so we get e to the y equals this. Now, here's a picture of the hyperbolic cosine. To get the inverse, we have to restrict the domain, and notice that x and y are both positive. There's a picture of the inverse hyperbolic cosine function. And so, since everything's positive, we can drop the minus, and we don't need absolute value. Hyperbolic cosine inverse is just the log of that expression without the plus or minus. Okay. Here are the other inverse hyperbolic functions. You may want to jot those down. These are logarithmic functions, which makes sense because the original hyperbolic functions were exponential in nature. Some integrals involving hyperbolic functions. These follow from the derivatives, and here they are, some in terms of the inverses and some in, you can rewrite all the inverses in terms of logs. They only did that with the one for hyperbolic cotangent. Okay, so here are some examples from your text. Number 6, here's a function, and I rewrote it using parentheses, although they're not considered necessary, just to clear up what is meant by this. It's the log of the sinh of 3x. And they want you to take the derivative, and so we just use the chain rule. 1 over what's inside the log times the derivative of the inside function, and then the inside function also has an inside function of 3x, and so we have to multiply by 3. Notice that cosh, remember, is the derivative of sinh. And then if we clean that up, cosh over sinh is the hyperbolic cotangent. So we can clean that up a little bit. Here's another example, number 12. The sinh of x to the 4th power. This is what's meant by that, same as with regular trig functions. And so using the chain rule, the 4 comes down, we reduce the power to 3 and multiply by the derivative of sinh, and that one can't really be cleaned up or changed much. Number 16, integrate cosh squared of 3u. Well, now you may remember from previous lessons that when you have cosine squared, you have to use an identity. Well, there's a similar identity in your book for cosh squared. It's 1/2 cosh double the angle plus 1. These are very similar to the old identities, it's just the plus and minuses are different. So that we can integrate with the reverse chain rule. We'll have to have a 1/6 in the front of the antiderivative of cosh to make up for that 6. So we keep the 1/2, we get 1/2 sinh of 6u. I'm sorry, did I say 1/2? I meant 1/6 of sinh 6u plus, and then the antiderivative of 1 is u. Aha, you thought I forgot the plus c, didn't you? Plus c. All right, here's another example from your book. This time it's an integral. And again, there are parentheses around the log x inferred. You don't really need them. And this is a u sub problem. We'll let u equal log x, and conveniently the derivative of u is there, 1 over x dx. And so we rewrite that as simply sinh u. The antiderivative of sinh is cosh, and then don't forget your plus c, and don't forget to put the expression back for u. U was originally log x, and you may or may not use parentheses as you see fit. Number 38, they want you to take the derivative of this, I believe. So using our handy dandy notes and the chain rule, the -1 comes down. We reduce the power to -2, and then the derivative of hyperbolic tangent is 1 over 1 minus the quantity squared. And then that quantity also has a derivative of 3. And that can be cleaned up a little bit, but not much. Okay, another example, number 42, a definite integral. Now, this one you could just do using partial fractions. But in this exercise, they want you to use hyperbolic functions. So looking at our list of antiderivatives, this is the one that it reminds us of. Notice that we use hyperbolic cotangent if the absolute value of the indices is greater than 1, which they are, 5 and 10. And we would use hyperbolic tangent if those numbers were like a half, and 2/3 or something less than 1. So now we need to rewrite it. We want x to equal 4u squared, so we can get that 4 out of there. And then x is 2u, dx is 2du. So substituting, we get 2du for dx, and we substitute 4u squared for x squared. And then you have to change the indices because u is a half of what x was. And then factor out the 4 and reduce the 2/4 to 1/2. And then that equals 1/2 hyperbolic cotangent of u from 2.5 to 5. And then I change to the log form of hyperbolic cotangent because I don't have a hyperbolic cotangent button on my calculator. Some calculators do, but mine does not. And again, the numbers are still 2.5 to 5. Combining the halves and plugging in the numbers, we get an approximate value for the integral of -0.110458. Now let's just peek at the graph of the original integrand. And I think it does make sense that that integral would return a negative value from 5 to 10, and a very small one at that. Example 46. We have x, the integral of x divided by the square root of x to the 4th minus 1. Well, that x is probably the derivative of something, and so that's a hint to use u equal x squared. That way du is 2x dx, and we're good to go. So now we've got 1/2 du replacing x dx. We've got u squared replacing x to the 4th. And that one, if you look at your handy dandy list, is the integrand there is the derivative of hyperbolic inverse, the inverse of hyperbolic cosine. And so that's a perfectly good answer. We could just go ahead and put our x squared back in for u, and that looks great to me. But I looked in the back of the book, and of course they had to change it to the log form. So if you change to the log form of hyperbolic cosine, you get that for the u antiderivative, and then replacing u with x squared, you get this as another equivalent final answer. Okay, I promised you earlier on that I would show you why hyperbolic cosine equals the expression using e. So instead of theta, I'm using t. I just like t better than theta for some reason. And so I need to show that this is in fact true. So there's my picture with the right branch of the hyperbola, the unit hyperbola, and its equation. And cosh t is the x coordinate, and the area there is t over 2. So if we used integrals to figure out that area, it would be the area of that triangle minus the area under the hyperbola. So that means t over 2 has to equal 1/2 xy minus the integral from 1 to x of the hyperbola. And if you solve x squared plus y, x squared minus y squared equals 1 for y, you get y equals the square root of x squared minus 1. And I had to use a different variable instead of x because I'm going to be substituting x. So I just used u. It's called a dummy variable. So anyway, the equation of the branch of that hyperbola is the square root of u squared minus 1. Okay, so the next step, I need to solve that integral. So I use trig sub. I let u equal secant w. du is secant w tangent w dw. And then I also replaced y with the square root of x squared minus 1 in the first part of the area. Okay, deep breath, deep breath. So now I used an identity for tan squared w, made it equal to secant squared minus 1. Now the reason that's a plus is I distributed the negative in front of the whole thing. And then we have done these two integrals before. That secant cubed one is a pain in the neck, so I just used the formula in the front of your text rather than doing it again, which would have been another 2 or 3 pages. And also the antiderivative secant w is also listed in the front of your text. Now notice we have the log of secant w plus tangent w twice, so I'm going to combine those. And at the same time, take a look at the triangle. We have the secant, or rather the, okay, I forgot, I have to go back and look. We said that u was a secant of w. So if I use x for u, the secant of w would be the hypotenuse over the adjacent leg. So that's x over 1. And then solving for the other leg, we get the square root of x squared minus 1. And so I can fill in for secant w x, and for tangent w, the square root of x squared minus 1. And combine those two log quantities of secant w plus tangent w. So doing all of that, I get this expression. And then it's just a matter of canceling those. That was handy, huh? Multiplying through by 2. And then because that expression, x is always positive in the unit hyperbola, so we don't have to worry about the absolute value. So we can just take the anti-log and drop the absolute value. And then subtract x from both sides. We're not quite done yet. And then we're going to square both sides. And the x squareds cancel. Yay! And so then we can move the 1 to the left and the 2xe to the t to the right. Finally, well, not finally, but almost finally, take a deep breath. We divide by e to the t, and then by 2, and there we have it. And remember, x was the hyperbolic cosine. And we can show that y equals e to the t minus e to the negative t over 2 in a very similar fashion, but let's not do that today. So that's the end of chapter 6. Next, we will begin our study of vectors in 2 and then 3 dimensions. And that will lead us into our multivariable topics. We're going to do things like slope fields in 3 dimensions. Won't that be fun? So now it's your turn to do some example problems in section 6.9. Have fun.